Hey everyone, and welcome to The Explainer. Today we're diving into one of the most rapid and, frankly, fascinating technical ascents we've seen in modern AI. We are tracking the lineage of Alibaba's Qwen-VL open source models, specifically from 2023 up to 2026. And this isn't just a story about a model getting bigger. It's really a masterclass in how precise, systematic engineering choices can completely redefine an industry standard.
Think back to 2023 for a second, right? Proprietary models were absolutely dominating the vision language space. Open source models, well, they were really struggling to keep up with complex, real-world tasks. Yet within just 36 months, the Qwen team made a series of highly specific architectural bets that didn't just catch them up. They literally created a master blueprint that the entire open ecosystem ended up copying. So how exactly did they pull that off? Okay, let's dive into this. Here is our roadmap for the explainer. First, we'll identify the 3 multimodal gaps. Second, we'll look at the generational evolution. Third, we're unpacking the M-ROPE math. Fourth, mastering dynamic FPS video. Fifth, structured agent outputs. And finally, deploying the standard.
Let's start with Section 1, the 3 multimodal gaps. We need to set the stage and look at the landscape back in August 2023.
At that time, models like Llama 1.5 and Blip 2 were really hitting a wall, and the Qwen team identified a threefold gap. First up, resolution. Models were stuck at 336 by 336 pixels. Now that might be fine if you're just identifying a dog in a photo, but it is utterly useless if you're trying to read a Chinese language invoice or a super dense spreadsheet. Second, video. Early approaches like Video LLM basically just stacked per-frame encoders and fed them to the language model. It worked for tiny clips, sure, but it completely lacked true temporal flow from multi-minute videos. Third, structured output. These early models emitted messy, free-form text. But if you want to build a real computer agent, you don't want a paragraph of text. You need actionable, deterministic JSON. These 3 limitations were totally crippling for real-world utility. Moving on to Section 2, the generational evolution from 2023 to 2025. Let's move to the timeline and see how this builds, because it's pretty wild. Starting in August 2023, Qwen-VL launched, bumping resolution to 44 by 4048, which was state-of-the-art for an open model at the time, and introducing grounded bounding box outputs. Then comes the massive leap in September 2024 with Qwen-2VL. They completely rip out the fixed resolution stack and introduce native dynamic resolution, along with something called M-ROPE. Just a few months later, February 2025, Qwen 2.5VL fundamentally changes video processing with dynamic FPS and explicit JSON tool outputs. And by November 2025, with Qwen 3VL, they stabilized the entire master architecture. They basically stopped reinventing the wheel and just started scaling it. All right, Section 3, unpacking the M-ROPE math, specifically looking at 3D rotary embeddings. So, what is M-ROPE? It stands for Multimodal Rotating Position Embedding. To really get why this is genius, you've got to realize that language models historically think in 1D, literally just a single timeline of text tokens. But an image has height and width. A video has height, width, and time. M-ROPE natively turns that 1D position embedding into a 3D grid. It splits the model's internal data, the hidden dimensions, into temporal, height, and width bands. It's almost like giving the AI a native 3D coordinate system to work with.
And this table brilliantly illustrates the difference. Classical rope uses a single unified band and a 1D mapping that's meant solely for text. M-ROPE, on the other hand, splits the mapping into that 3D coordinate system, time, height, and width. Let's put that into perspective. Say your hidden dimension is 96. M-ROPE efficiently assigns 32 dimensions to time, 32 to height, and 32 to width. For an image, time is just 0. For text, height and width are 0. For video, all 3 are active. The immense benefit here is that one single positional encoding handles text, images, and video natively without branching code or having separate positional embedding tables. It's just incredibly elegant. Let's shift gears to Section 4, mastering dynamic FPS video and absolute time alignment. This right here is where they made a huge leap. They stopped just feeding the model frame 1, frame 2, frame 3, and instead introduced absolute time tokens. The model actually sees a tag, like time 0.04, time, interleaved right in with the frame tokens. It gains true temporal understanding. It doesn't just know the sequence of events. It knows that, hey, at exactly 004, the CAD jumps. It literally understands seconds. But as we all know, video is super heavy, and context windows, even the really large ones, fill up fast. So they introduced dynamic FPS sampling. Here is the exact logic the model uses.
Step 1. It computes the maximum frames per second it can afford based on your token budget and the video duration. Step 2. It picks a target FPS, usually 1, 2, 4, or 8. Step 3. It adjusts this based on motion heuristics. So if it's a super slow security camera, 1 FPS is totally fine. But if it's a high-action sports clip, it ramps up to 4 or 8. Finally, Step 4. It samples uniformly and inserts those absolute time tokens we just talked about. This smart sampling means a 60-second action sequence at 4 FPS comes out to about 19,440 tokens, which is perfectly manageable within a $32K context budget. For developers, this means massive savings in compute costs without sacrificing any of the model's understanding of the video. Moving to Section 5, Structured Agent Outputs. This is where we get into agent-ready JSON.
Highlight the visual contrast here. The old way, the lava way, was to spit out free-form text with coordinates just shoved inside tags. If you were coding an application around this, you had to write messy regex expressions to parse it. And if the model hallucinated even a single parentheses, your code broke. The Qwen-VL way is deterministic JSON tools. It was explicitly trained on tool call data, so it outputs clean, flawless JSON. Tool is click, coordinates are 380, 220. This makes it agent-ready right out of the box. A real game changer for developers.
Which brings us to our final part, Section 6, deploying the standard and looking at the real-world impact. Now, what's really interesting about this slide is the sheer dominance of these breakthroughs when you look at real-world benchmarks. Take the ScreenSpot benchmark, for instance. This tests a model's ability to act as a GUI agent and accurately ground itself on a screen. The mighty GPT-4o sat at 38% accuracy. Qwen-VL pushed that to 55%. But because of that strict JSON output and dynamic resolution we just discussed, Qwen-2.5VL absolutely crushed the benchmark, leaping to an incredible 84% accuracy. That's not just a slight improvement, guys, that is a total paradigm shift in reliability. And that brings us to the culmination of this whole journey. By the time Qwen-3VL arrived in late 2025, the foundational architecture had completely stabilized. The recipe was set in stone: a 2D rote vision transformer encoder, native aspect ratios, which means absolutely no more weird cropping or stretching, and explicit agent training targets. The Qwen team had definitively written the master architectural blueprint for open-source vision language models. Every future generation from here on out, it's about scaling compute and data, not reinventing the structural primitives. So what does this all mean? The Wild West of multimodal architecture design is basically settling down into a proven standard, which leaves us with a massive question for the future. If the blueprint is now written and stabilized, where exactly does the next big breakthrough come from? Will some researcher find a completely new algorithmic design that shatters this paradigm all over again? Or is the future of AI going to be driven entirely by feeding unimaginable, staggering scales of data into this exact same architecture? It's a truly fascinating space to watch. Thanks for joining me on this explainer, and keep learning.